have enough room, I can slide by you, we can move here, I can move there. They start moving. When they start moving, that means there starts to be some chaos added into it. Everything's not in an ordered arrangement. There's much more motion, and there's a lot more ways the particles can be arranged. If all the particles are stuck in a position, there's really only one way they can be that way. But if they're sliding past each other, there's much more chaos, okay? So if we go from liquid to gas, we see a tremendous amount of increase in chaos because the particles get further and further and further and further apart. Okay, a lot more movement. If we go from fewer gas particles to more gas particles, this also holds true because the more particles you have, the more possible ways you can arrange those particles. Okay, so all this leads us to something called a microstate. A microstate is one of the possible ways that a set of things can be arranged. Things like freedom of motion and differences in the way that the energy can be distributed are all part of the microsystem. So think about having 10 objects in a room and think about the ways that you can arrange those 10 particles in a room. Now, if you put those all on battery-operated remote control vehicles and you start whiz them around the room, the way that they're arranged starts changing quite rapidly. Okay? So, a macrostate is a given set of conditions, pressure, volume, temperature, number of moles of particles, and a macrostate is made up of a lot of possible microstates. Okay? Entropy is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components in the system to achieve a particular macrostate. Now, in the room I'm in right now, okay, there's lots of different ways for all the gas particles in this room to be moving around. Okay? There are lots of ways for the particles to be spread out throughout the whole room. There are very few ways to have all the particles plastered against the board here. So there are more ways for this room to have the gas particles spread than have them concentrated. That's what we're talking about when we're talking about kind of macrostates and entropy. Okay? Scientist by the name of Boltzmann was working on entropy, S, and he was relating it to, his famous equation is S equals K times the natural log of W. It's on page 801 in your textbook. Don't panic. I'm not going to make you repeat it. Okay? Scale up for me. So we're going to look at possible ways that energy can be dispersed. Flip over to the... Okay, guys, go up here. Okay, if we think about having 4 particles and a 2-sided chamber. Okay, right now the valve is open. Okay, if I have those 4 particles, I could have all 4 of them over here on the left-hand side, all over here on the right-hand side, or I could have 2 here, 2 here. Now, if I was to number these 1, 2, 3, and 4, there's one way to have them all over here. There's one way to have them over here, but I could have 1, 2 here, 3, 4 here. I could have 3, 4 here, 1, 2 here. I could have 1, 3, and 2, 4 here, or I could have 1, 4, 2, 3 over there. So if we look at the possible ways for the particles to be distributed between the 2 vessels, there's many more ways to have them spread out between the 2 than there are to have them all concentrated here, all concentrated here. So having them spread, 2 on this side and 2 on this side, is going to have more entropy. nature has a tendency to move toward more entropy. Okay? Now, the book goes and talks through what I just talked through. Okay? So, 1, 2, 3, 4, 2, 3, 1, 4, 1, 3, 2, 4, 2, 4, 1, 3, 1, 4, 2, 3, 3, 4, 1, 2. So there are 6 different ways to have the particles spread out, 2 on each side. That's more entropy. Okay? So just so you get the idea. Now, the second law of thermodynamics says all real processes occur spontaneously in the direction that increases the entropy of the universe. Okay? No, don't flip it. We just went over that. So, let's talk about phase changes in entropy. If we look at practice problem 18.1, let me kind of talk you through it. If we think about phase changes, if we think about things happening spontaneously, okay? Is the boiling of water spontaneous? Well, to have water boil, I've got to have it sitting on top of the stove and continuously input energy. If you turn the stove off, the water stops boiling. So that change is not spontaneous. But if we think about, no, I don't quite want to go there yet. Let's see. Let's talk about phase transitions. Solid to liquid, liquid to gas, solid to gas. Depends on what kind of conditions you're under, whether the process is spontaneous or not. I don't really like that question very much. Let's talk about the changes in entropy here for a second. Let me get my train of thought all pulled back together, guys. In general, when we go from a solid to a liquid at the same temperature, so at the freezing/melting point, we see an increase in entropy. If we see going from the liquid to the gas, going from the liquid state to the gas state, increases entropy. Okay? So if I told you that I went from gaseous iodine to solid iodine, you would say that would be a decrease in entropy. If I went from liquid water to solid water, that would be a decrease in entropy. Okay? So just thinking about what direction entropy is changing. Now, when we think about entropy and we're thinking about thermodynamics, we're going to talk about reversible processes. A reversible processes is a process that we do in infinitesimally small increments so that we can go backwards when we need to. So we can reverse direction upon an infinitesimally small change in some property. Okay? That's going to be very important for thermodynamics because thermodynamics and our changes in state are all based on a reversible process. Now, popping a balloon is a non-reversible process. Okay? Whereas if let's see, what would be a reversible process that you would recognize? I can melt water and I can freeze water. Okay, I can melt an ice cube, I can freeze water into an ice cube. That's reversible. But if I pop a balloon, I can't put the pieces all back together. Another example of an irreversible process would be something like stirring cream into coffee. If you spin the spoon the other direction, it doesn't gather back up the cream into one spot in the coffee. Okay? So let's talk about the third law of thermodynamics. Third law of thermodynamics says that a perfect crystal of a substance at 0 Kelvin will have an entropy value of 0. 0 Kelvin, remember, is absolute zero, and it's the theoretical point where all motion stops. Okay? Because of the third law, we can actually get an absolute value for entropies. So we know as temperature increases, the motion of the particle increases, entropy has to increase. As we change from solid to liquid, we see an increase in entropy. As we go from liquid to gas, we see an increase in entropy. We know the more complicated the structure, the more entropy a particle has, because remember, it vibrates and rotates. So the more complicated the structure, the more different ways the atoms can move relative to each other. If we dissolve a solid up into liquid, we see an increase in entropy for the solute, and usually an increase in entropy for the solvent. Notable exception is when we dissolve a salt up in water. Water actually becomes more ordered around the ions. It forms coordinate covalent bonds, so the water actually becomes a little bit more ordered when a salt dissolves up in it. When we mix two liquids together, we always see an increase in entropy. And when a gas dissolves up in the liquid, there is a decrease in entropy. Okay? All right. Now, let's move on. So, unlike enthalpies, delta H, where it's almost impossible to get an absolute value, for entropies S, we can get absolute values because of the third law. Okay? Entropy values are positive because we have an increase in entropy as we move from 0K up. You can't have a negative entropy for something.